So, I will continue with my discussion of mathematical concepts that we need to build up the simplex algorithm. And let me, I had in the last lecture I had defined in linear independence, dependence, and then concept of a basis and so on. So, let me just go back to one of the things that I sort of left out, and we can come back to it. So, this is augmentation theorem. So, the idea here is that if you have a subset of linearly independent vectors which do not form a basis, then I can always add some more vectors to it and get a basis formed. That means, if the number of linearly independent vectors is less than the dimension of this vector space, then I can always add some more vectors to it, so that it becomes a basis. This is the idea of a augmentation theorem. And what it says is that suppose A1 to AR are linearly independent, vectors in Rn, and R is less than n, then the set can be augmented by adding n minus r more vectors, so that the augmented set forms a basis for Rn. Okay. So, this is the whole idea. I will just give you the idea behind it without actually giving you the proof. So, what is being said is that suppose you take two vectors, or let me take the vector 1 0 0 and 0 1 0 to take a simple example belonging to Rn. We know that these two vectors are linearly independent, right, because if you take a linear combination then and it is equal to 0, then you immediately see that your C1 will be 0 and C2 will be 0. If I take C1 times this plus C2 times this vector equal to 0 vector, then it will always imply that C1 and C2 both have to be 0. Okay. So, therefore, this is a linearly independent set. I can augment it, and what is the idea behind it? The idea here is that you see these two vectors, if you take this, see, let me take three dimensional thing. So, this is x1 x2 and x3. So, the three axes, and here 1 0 0 1. So, 1 0 0 is this is the unit vector in this direction, 0 1 0 is the unit vector in this direction. So, actually any linear combination of these two vectors represents your x1 x2 plane, right, all over. So, if I take any vector which is not in the plane, then certainly it cannot be expressed as a linear combination of these two vectors. Figure it out, it's very simple. So, if I take a vector, and what does it mean to have a vector which is not in this plane? That means a vector which is not in this plane will have its third component non-zero. That means any vector of the kind 0 0 x3, this also belongs to R3, and 0 0 x3, oh I am sorry, this should be 3, these both belong to R3. So, this does not belong to the linear combination of the vectors 1 0 0 and 0 1 0. Okay, so I have shown you this. So, this is how one can go on augmenting a set. That means, if you have a set of linearly independent vectors, find a vector, and since R is less than n, obviously this cannot be a basis. That means, it cannot be a spanning set for Rn. So, therefore, there will be vectors which are not in the linear combination of these R vectors. So therefore, I can find one, add it to the set, that will remain linearly independent. Again, if R plus 1 is still less than n, I can find a vector which is outside the linear combination of the augmented set and add that vector to it. So the process goes on like this, and the proof requires a lot of time. So therefore, we can simply, since we need the result, I am just giving it to you. So to say that a linearly independent subset which does not form a basis for Rn will always, it will be always possible to add vectors to it and form a basis out of it, right. So therefore, you see that this is this, and so what I am saying is that 1 0 0, 0 1 0 and 0 0 x3 are linearly independent, and since they are 3, they will form and forms a basis and form a basis for R3. So this is the idea behind augmentation theorem, and later on we will show you how we can extend a basis for a degenerate basic feasible solution, or we can demonstrate that there can be more than one basis corresponding to one degenerate basic feasible solution, and so on. Yeah. Okay. So this was your augmentation theorem. Let us get to some more concepts here. So I want to just quickly revise, because you have already, say for example, what do we say, a closed set? Now there can be a closed set. Okay. What we mean by a closed set is that all its limit points are in the set. Okay. Or you can say that you can also define the boundary of a set, and you can say that if the boundary is all in the set, then it is a closed set. Whatever it is, say for example, a very easy way of saying, if I define a set by saying that S is equal to, let's say, x belonging to Rn, such that some a1 x1 plus an xn is strictly less than b. Suppose I have the strict inequality, then you can see that this is not a closed set, it's an open set, because the boundary, that means I can take a sequence here and it's possible that the sequence will converge to b. When I take this summation here, add it up, it will converge to b, and so that limit point of that sequence will not be in the set, because I am taking only all those points in S for which this is satisfied as strict inequality, right. So in other words, when you take this set, when you take the feasible region for the linear programming problem, we say x belonging to Rn such that Ax is equal to b, x greater than or equal to 0. So we have equality sign. You have m equations here, and you have n inequality, equality. Zeros are also allowed. The variable can take the value 0. So this will be a closed set, right? Because I am allowing equality constraints also, whereas here I am not. So I have not written down a rigorous definition for a closed set, but we can say the definition of a closed set would be if all the limit points of a set are in the set, we say it is a closed set. We say it is a closed set. Okay, and if all the limit points are not in the set, then it will be an open set. Okay, a bounded set. So S contained in Rn is said to be bounded, if norm x is less than some m for all x belonging to S. Okay, we have already introduced the concept. My Rn, that was in my earlier lecture when I was talking of the mathematical concepts. I defined certain operations on Rn, and through inner product we also define the norm of a vector on Rn, and so we are saying that if the norm or the length of a vector is less than some pre-specified number m, then or I can find an m such that norm x is strictly less than m for all x in S, and we say that the set is bounded. Okay. So, for example, if you take the set, yes, something like this. Again, I will draw it through the, suppose you have this, right. So, if my set is something like this, then you see this is extending to infinity. So, therefore, if you give me any number, I will always be able to find another number. So, I will be able to find a vector in this set whose length is or whose norm is more than the number that you have given me. So, I will always be able to extend it, right. Okay. So, this is an unbounded set. Okay. And now let me go on to, yeah. So, the next point that we want to make is, yeah, look at the, because again remember all my definitions and results are such that they relate somehow to my linear programming problem. Okay. So, for example, if you look at this, yeah. So, now let me define a dimension of a subset. Dimension of a subset S of Rn. So, the idea here is, see, so far when I defined the dimension of a vector, it was of a vector space. That means we had a notion of linear independence and so on, and it was, we defined the dimension of a vector space or a subspace, but it had to satisfy these certain criteria for, or the axioms of a vector space. So, we want to define the dimension of a subset S of Rn. So, to do that we need to define the dimension of an affine space, because I can only define the dimension of a subset through the dimension of a affine space which can. Now, what is an affine space? This is the displacement of a subspace by some vector. That is, if Q is an affine space, then Q can be written as x naught plus W, where x naught in Rn is some vector, a fixed vector, and W is some subspace of Rn. So, any affine space, that means you are actually taking a subspace W, displacing it by the vector x naught, and then you get an affine space. So, this stops from being a subspace, because obviously 0 vector does not belong to it, right. So, then now for example, you can see that if you take W to be a straight line passing through the origin in R2, then this is a subspace of dimension 1 in R2, right. So, you take this straight line which is passing through the origin. So, this is the subspace in R2, W is the subspace. Now, I take a vector x naught, a fixed vector, and so I have displaced W through the vector x naught. So, therefore, what we are trying to say here is that if you take now just take some vector small w here, and then you want to look at the vector x naught plus w. So, then see, you complete this parallelogram. So, this vector would be your also w, right. So, then the sum would be given by the vector OP, which is x naught plus w, w belonging to this. So, any point on this displaced subspace, displaced straight line can be obtained as x naught plus some w in capital W. So, this is the concept of a affine space, right. And then we say that the dimension of Q, of the affine subspace Q, is the same as the dimension of the subspace W, which is defining it, right. And then so here as an example of a affine space which you already have come across is solution set of a non-homogeneous system of linear equations is an affine space, right, because you know, when you take the non-homogeneous system, you have a particular solution, and then you take the homogeneous part. So, that solution space is a subspace, and so you get the solution space of a non-homogeneous system, which now becomes a affine space, right. And so, now we come back to the defining the dimension of a subset P of Rn, and that would be the smallest dimension of the smallest affine subspace containing P. So, this is the concept which we have to also, and of course, like which is smallest, I have not written it properly. smallest, right. And let us say we will not spend time here on actually telling you how to get the smallest, but when you come across the concept of defining a subset, a dimension of a subset, I suppose this will be clear. And mainly we would be dealing with dimension of the feasible region corresponding to a linear programming problem. So, there should be no problem, and I will try to explain that here. So, therefore, we want to find out the affine space which contains a subset, the smallest affine space, and then the dimension of that affine space would be the dimension of that subset, right. Now, so let us look at the feasible region for an LPP, and the standard form, this is your LPP. Then you will first look at the subset, or the where x equal to Rn, Ax is B, right. Now, this is the affine space I told you, because the solution space of a solution set of a non-homogeneous system of linear equations is an affine space, right. So, this can be written as x naught plus w, where x naught is a particular solution, right, A x naught is B, and w is the solution space of the homogeneous system, A x equal to 0, right. This is a subspace. So, the solution space solution set here can be obtained as a particular solution plus the subspace, which is the solution space of the homogeneous corresponding homogeneous system, right. Now, you can immediately see that F is in S, and S is the smallest affine space containing, because in F now you require the solution should be all non-negative, right. And so, this will be the smallest subspace affine space containing F, and therefore, dimension of F will be dimension S, the affine space containing F, and the dimension of S is nothing but dimension W, where we are saying W is the subspace of the containing all the solutions for the homogeneous system, right. So, this is what. So, therefore, now we know how to define the dimension of the feasible region corresponding to a linear programming problem. Okay. A special kind of affine space which we will be using very often is a hyperplane, and a hyperplane is defined by one non-homogeneous equation. So, for all x in Rn which satisfy sigma aj xj equal to b, j varying from 1 to n. So, this will be my hyperplane, and we can immediately see that this will again be some x naught, which is, that means which satisfies this, it is a particular solution, a particular point in H, and then plus solution space of homogeneous linear equation sigma aj xj equal to 0. So, this is only one linear equation, non-zero, because our ages are not all zeros. So, therefore, the dimension of the dimension of the solution space would be what here? The dimension of the solution space will be n minus 1, because only one linear equation, homogeneous equation is describing this set. So, therefore, the dimension of the solution space is n minus 1, and so dimension H is nothing but dimension solution space of sigma aj xj equal to 0, which should be n minus 1. So, hyperplanes are special kind of affine spaces which have dimension 1 less than the dimension of the space in which you are working. So, we would be talking of supporting hyperplanes and so on. So, this is the idea, and it helps to understand the geometry, and of course, the dimensions helps you to visualize the things better. And so, the idea now we will go on to defining your 3-dimensional polytopes and so on, and then we will restrict ourselves to 3-dimensional here, of course, but you can have, and then I will talk of different facets and so on of the polytopes. So, now let us continue with some more definitions. I am trying to illustrate and so on, so to break the monotony. Just do not want to go on feeding you with definitions all the time, but it helps to collect together all the theory that we need, so that we keep on referring back to it, and then when we develop the algorithm, we do not have to all the time go back and say, okay, this is what we have to define. So, it is better that I do it all in the beginning. So, now let me define another concept, and that is of convexity. This is very important, and you see how much this concept helps to simplify the concept of the whole theory that we are going to develop. So, first of all, I will say that if you have, let x1, x2 belong to Rn, then lambda x1 plus 1 minus lambda x2 is lambda x1 plus 1 minus lambda x2 for lambda greater than or equal to, need I say? Yes, okay. I need to say it's between 1 and 0, not just. So this for 0 less than or equal to lambda less than or equal to 1 is a convex combination of the 2 points of x1 and x2. And as you vary lambda, you get all possible. So in other words, geometrically you can see what it means. It means that if this is a point x1 and this is a point x2, and as you vary lambda, you get all the points on the join of these 2 points, isn't it? The line joining these 2 points, you get all the points. Now if lambda is 0, then you get the point x2. That means you get this end. And if lambda is 1, then this is 0 and you get the point x1. And for all values of lambda between 0 and 1, you will get points on the join. Right? So this is called a convex combination of 2 points. Now we immediately we can define a set to a convex set, and that is when a set C Rn is a convex set, if and only if it contains all its convex combinations, Okay, so it's a convex set if it contains all its convex combinations. That means I take any 2 points in C, I take the line joining the 2 points, that the whole line should be in C, and this should hold for all points in C. Then we say that the set is convex. Now for example, if you take this set, then I take a point here, and I join the 2 points, then see, part of the line is not in the set. So it will not satisfy this definition, right? Because there are holes, indentations. Similarly, if you take a ring, then and if you say that this is you're considering this set ring, then I take a point here, the whole line is not in the set. So this is not a convex set. That means a convex set has to be without any holes or indentations. So a circle, that means inside of this circle, and if you include this, then this is a convex set. Then you can also have, yes, so if you take this set, you see, because it's enclosed by straight lines, therefore there are no holes, and I take any 2 points on the set, the join will be in the set. So this is the idea of a convex set. Okay. Now you can also extend this notion to a finite combination. And I said if and only if. See here, that means if a set is convex, then all convex combinations of any 2 points in the set must be in the set, and if the set is convex, then this happens, and if all convex combinations of any pair of points in the set are in the set is convex. Okay, so it's both ways I can define. Yeah, one can have a more general concept here also. So you can extend this notion. You can also say that convex combination of a finite number of points, of a point, say x1, xk. Yeah, I've stopped using the word, this sign of a vector, because it's now understood, right? So is a convex combination of a finite number of points, this is something like this. lambda I xi, I varying from 1 to k, where summation lambda I is 1 and 0, I varying from 1 to k, and this is for all I. Okay. So, just extend the notion. For example, when k is 2, I get a convex combination of 2 points, and if k is more than 2, then I get this. So, the lambdas must add up to 1, and they must be both, they must all be lying between 0 and 1. So, this is the convex finite, and you can see that this is more general, and if a set contains all possible convex combinations of a finite set of points in the set, it is convex, and vice versa. And by iteratively using this definition, you can show that the two concepts are the same. Okay. So, this gives you another way of defining a convex set. Okay. Now, the thing is that, so therefore, I can state a more general theorem and say that if C contains all convex combinations. So, actually convex combination implies that you are taking a convex combination of a finite number of points, but maybe one can state it also, if C contains all convex combinations of any finite set of points in it, then C is a convex set, and vice versa. Same thing, if and only if. That is, if C is convex, it must contain all convex combinations of any finite set of points in it, and if it contains all finite combinations of convex combinations of finite set of points in it, it is convex. Okay. Now, let me define another concept, which is convex hull. So, a convex hull would be, so convex hull of a set S. So, S is in Rn, then we say that this is a convex hull. Actually the notation, okay, let me make the correction, because remember I have used this for all possible linear combinations. So, here I want to make, so maybe this would, so this is a convex hull of S, and this is collection of all possible convex combinations of points in S. Okay, I have dropped the word finite because it's understood. So, if you take all possible convex combinations of points in S, that becomes the convex hull, and by definition, and this is a convex set by definition. See, remember, I gave this definition for a convex set, then I said that, and this is sort of a lemma or a theorem which says that if you can also say that finite, you take a convex combination of finite points in S, and this convex combination is in S for all possible such combinations, then C is convex. So, actually I use this to prove this, and now because of this result, we can say that S is a convex set by definition or by theorem or whatever it is. Okay. This is a convex set, and convex hull of a finite number of points finite number of points, we would want that all possible convex combinations should be within the set, within the convex hull. So, here if you take for example, say these are some finite number of points and like this, but we want all possible convex combinations of these points to be in the set. So, then I will draw these lines. So, to make sure that no convex combination of these points is outside the set, and this will be this and this is this. So, then this will be my convex hull of this given set of finite number of points. For example, for this one I would, if I want the convex hull, then I will have to include this also. Yeah. So, the whole thing, then it becomes a circle and this is a convex set. So, convex hull, when you take the convex hull, it actually fills in the gaps, and all the holes and all the indentations that are there in the set, they get filled up and it becomes a convex set, right. So, now you can also define intersection of intersection of any number of convex sets is convex. Okay. So, intersection of any number of convex sets is convex. It is very by using the definition you can immediately prove it, and so by virtue of that, if you look at the feasible region for LPP, then you have Ax equal to B, x greater than or equal to 0. So, how many convex sets you have? Each hyperplane is a convex set. Why is so? Here you see each of the equations, summation Ai j x j, j varying from 1 to n equal to Bi is the ith constraint, is the ith equality, right. So, this constitutes a hyperplane and it is a convex set, right, because if you take any 2 points satisfying this, then they are joined, that is a concept of a hyperplane, right. So, this is a convex set, already the convex set. So, f, and then when you take xi greater than or equal to 0, what do you get? See here, I should have maybe spelled this out, that if you have, let us say, taken, or okay, this is x1, x2, x3. So, when you take a plane, hyperplane like this, right, it is a 2-dimensional thing, you can imagine it extending like this, then this hyperplane actually gives you 2 half spaces also, right, half spaces. So, when you have that summation A j x j, j varying from 1 to n is equal to B here, then there will be set of points which satisfy the constraints as strict A j x j, j varying from 1 to n greater than B, and there will be a set of points which satisfy it with less than B. So, these are the 2 half spaces that a hyperplane defines, and you can see that this is convex, there are no holes, there are no breaks, and even analytically you can show that these are convex subsets, right. So, here you have m such sets, convex sets here, then each of the non-negativity constraints also gives you a half space, right, xi, because xi equal to 0 will be a hyperplane, and then xi greater than 0 is other 1/2 of the hyperplane, and so here you have that means f can be looked upon as intersection of m plus n convex sets, and that gives you the okay. So, that gives you a convex set. So, this is what we mean, intersection of any number of convex sets is a convex set. So, I showed you that the feasible region for a linear programming problem is a convex set, and in fact we and this is a special kind of a convex set which we want to give it a name. In fact, F is a polyhedron. F is a so we give it a name because this is a special kind of a convex set, because it is defined by linear equations and inequalities. So for such convex sets we give a special name, and in general you can also say that, I mean, a general form of a polyhedron. So a general form of a polyhedron can be defined as, and let me call it P, right. So I will distinguish between a general polyhedron and the polyhedron which corresponds to a linear programming problem. So Px belongs to Rn such that Ax is less than or equal to B. So what we are saying here is that even if there are some greater than or equal to kind, which is the non-negativity constraints, they can be part of this here, right? Because and I'll try to show you how you can write, because I can multiply this by minus sign. So this constraint, for example, can also be written as minus xi less than or equal to 0. Yeah, so it's not a big deal. I mean, I can take these as equations and inequalities, put them together, and in a more concise way you say that this is your description of a polyhedron, right? So we will mostly be dealing with polyhedrons, okay, in linear programming. Fine. And then if P is bounded, remember I defined, that means if I can say that there are no this thing here, you can bound the length or norm of every vector in P. If P is bounded, then P is called a polytope. And we will see the advantages of having a polytope also, because if the set is bounded, it gives you some special leverage to talk about the corresponding linear programming problem. Okay. Fine. Then you can also define, yeah, so now you have a polyhedron. That means essentially, and of course it's so much convenient to draw this thing in. So a polyhedron, what we are saying is something like this. So it is bounded by linear constraints, straight lines in 2 dimensions. In 3 dimensions it will be hyperplanes, and so on. So this is a polyhedron. So now, after having defined a polyhedron, let me now talk of subsets of polyhedron also, and some of them have a lot of significance in the development of the simplex algorithm. So HS be a half space defined by a hyperplane H, and I talked to you about the half spaces and how when every hyperplane will define 2 half spaces. And so if HS is a half space, then the set F, which is P intersection HS, that means the intersection of P with the half space, and it is a subset of H, then it is called a face of P, and H is called the supporting hyperplane. Let me give you an example here. Say for example, if you have a hyperplane like this, suppose this is a hyperplane H0, then you see the hyperplane has 2 half spaces on this side and this side. So the whole of the polyhedron lies in this half space, and the intersection of the intersection, or you can say that I will look at this half space. So half space and intersection P is this point A, and this point A is on the hyperplane H0. Therefore I will say that H0 is a supporting hyperplane for the polyhedron P, right, and the face F just consists of the point A. This is the idea. Now for example, if I take a hyperplane like this, suppose I take this hyperplane H1, then you see the half spaces are this and this, and the intersection of, if you look at this half space, then the intersection of the half space with the polyhedron is all of this, and not all of it lies on H1. Similarly, if you take this half space, the intersection of P with this half space is all of this polyhedron, and again it is not a subset of H1. So therefore, H1 is not a supporting hyperplane, right. Then similarly, if I take a hyperplane like this, so I am just trying to show you different faces that a polyhedron can have, and of course we will give you more examples by a better example by a three-dimensional polytope and so on. So here you see, if this is, you take this hyperplane, then the intersection of the hyperplane with this half space is only this part, right, this line segment, and this is part of H2. So again, H2 is a supporting hyperplane, and BC will be a face of the polyhedron that I drew, right. So this is the idea of a supporting hyperplane and a face, and then I will talk to you about, but before I start talking more about special kinds of faces, let me first define the dimension of a polyhedron, which is important. And again, here there are a little few ambiguities, but anyway, what we are saying is that the dimension of a polyhedron P, and remember the general definition that I gave you was Ax less than or equal to B, right, x in Rn, and then I am just defining a polyhedron by, and so I am calling these as the defining inequalities, and I had told you that the defining inequalities also, you know, there is a concept of a minimal number of inequalities that are defining polyhedron, and those things are there. But anyway, so let us hope that we have a minimal representation, and then I am talking of the dimension of a polyhedron. So if n is the number of variables, then the number of linearly independent inequalities defining P that are satisfied as equality by all the points of P, then I say that the dimension of P is n minus this number. That means if all points of P satisfy certain inequalities as equalities, and I take them to be linearly independent, then I take that number and subtract it from n, and then that gives me the dimension of P. Because again, if you can go back to, I talked about degrees of freedom and so on when you talk of a system of equations or inequalities, fine. So here for example, for the if F is your feasible region for LPP3, and remember I am also referring to it as a polyhedron, it is a convex set. So then when taking rank of the coefficient matrix to be M, then dimension of F will be n minus M, right, because I am assuming that all, so all the see the feasible region, the first standard LPP3 is in standard form, so M equations are there and the rank of A is M, so they are all linearly independent, okay. And so the rank dimension of F for the LPP3 is n minus M, okay. Now if no inequality is satisfied as equality by some points of P, that means that there exists a point x naught in P such that Ax naught is strictly less than B. If at least one point is there, then we will say that dimension of P is n, or that it is P has an interior, okay, or that P is a solid. So these are different concepts which mean the same thing, that we will say that P is a solid because it has dimension n, or it has an interior, right. Now for the LPP3, your feasible region is not solid, right, because its dimension is n minus M, right. And so there are points which satisfy the first M equations. So therefore it cannot be a solid, fine. Now let me define the definition of a face also, and then we will look at the examples here. So F is a face of P, then there exists an R by n submatrix of A prime of A, okay. That means you take some R rows and then A and B prime is the corresponding submatrix of B. That means here if I take suppose I take the first R rows, then I will take the first R components of B, or whichever R rows I take from here, the corresponding components of B I will take. So that that comprises of B prime, right. So then F can be described as a set of all points which satisfy these R inequalities as equalities. So A prime x is equal to B prime. So every face will be satisfying some inequalities as equalities, and then in that case dimension of F will be said to be n minus R, where dimension of P is n, right. So for example, when we define faces of F, we will have to take in place of n, we will write n minus m, assuming the rank of A is m, right? Okay, so now let's quickly just give you definitions of some particular faces. So the special kind of faces that I was mentioning is a facet which has dimension 1 less than the dimension of the polyhedron. An edge will be a face of dimension 1, and an extreme point or a vertex or a corner point is a face of dimension 0. Now I want to just translate this concept to the faces of the polyhedron of the feasible set for the linear programming 3 problem, right, we define. So, we know that the polyhedron f is defined by a x equal to b, x greater than or equal to 0, and we are assuming that the dimension of A is m. Therefore, this polyhedron has a dimension of n minus m, because the number of variables is n, and then a facet has to have dimension 1 less than the dimension of f. Therefore, it must satisfy the dimension is n minus m minus 1, which implies that one of the x j must be 0, because for f, you see, the inequalities are here. So, these are n inequalities, all these m equations have to be satisfied by all points of f. So, this is the nth these are the n inequalities. So, your facet must satisfy at least one of them as equality, right. So, this is it, and that means a facet will satisfy m plus 1 equations, m here and one of them, one of these inequalities as equalities. Then points on an edge, because the dimension of an edge is 1, that means it must satisfy n minus m minus 1 inequalities from here as equalities, which means that the number of positive components, number of components that are positive for points on an edge will be equal to n minus of n minus m minus 1, which means m plus 1. So, for points on an edge, the number of components that can be positive would be m plus 1, okay, because the dimension of an edge is 1. So, that means it must satisfy the dimension of f is n minus m. So, it must satisfy n minus m minus 1 inequalities as equalities, and for an extreme point, because the dimension of an extreme point is 0. So, it must satisfy n minus m, this number is okay. This is n minus m, right. So, n minus m components from here must be 0, because the dimension of an extreme point is 0. So, n minus m minus of n minus m should be 0. So, therefore, for every extreme point of f, the number of components that will be 0 has to be at least n minus m. Of course, if it is a degenerate point, then the number of zeros can be more than n minus m. Extreme point of P of a polyhedron P. Now, there can be one way, of course, I have showed you is that the extreme point is a face of P of dimension 0, okay. Or geometrically also we can define, because you see it is in a sense, since the hyperplane intersects it only at one point, therefore, you can also have this concept of a vertex or a corner point. So, these are the other names, and so an extreme point is also known as a vertex or a corner point of P, and we can give a geometrical definition of an extreme point, that is, if x belonging to P is an extreme point, of P, and x can be written as lambda x1 plus 1 minus lambda x2, if and x is this for some x1 x2 belonging to P and 0 less than lambda less than 1, then x is equal to x1 is equal to x2. I hope you can read this. I'll try to rewrite it. X2. Okay. So in other words, x, if it's an extreme point of P, it cannot be written as a convex combination of any two other points in P. So this was the concept of a vertex, and I showed you in the picture. And of course, the other definition was that it's a face of dimension 0 of the polytope. Fine. And so let us look at this example here. So there is a polyhedron described by these inequalities, right? And I have drawn the diagram here on the figure. You can see that, for example, this face on which the points 0, 2, 2, if you look at 0, 2, 2, it satisfies this as equality. Then 0, 3 by 2, comma 3 also lies on this face, and then this point 3, 0, 3, because 3 plus 3 add up to 6. So this is your first constraint as equality, right? And now, so according to our concept, you see, this is, if I take this equal to 6, this will be a hyperplane, and the whole of the polyhedron lies in those half space, which is, because here this is less than 6. So all points 0, 0 and everything, this is in the half space, which is less than 6, less than or equal to 6. So this is the picture, right? Then you can see that this face of the polyhedron is, because x3 is 3 for all 3 points. So this is the hyperplane. If you take the hyperplane x3 equal to 3, then it meets the polyhedron in this face, right? And similarly, this one corresponds to 2x1 plus x2 equal to 6. So this face, if you look at, then I have shown you, and yeah, this is another face which is x2 equal to 2, because all the 3 points lying on it have this second coordinate as equal to 2. Okay. So this is your 3-dimensional polytope, and you can see that if you look at the point, for example, 1, 1, look at the point 1, 1, then it satisfies all the constraints as strict inequality, right? 2 plus 4 less than 6, this is less than 6, everything. So this satisfies all inequalities as strict inequalities, right? As strict inequalities, and therefore, the first thing is, therefore dimension P is 3, because now P has an interior. So I talked to you about it, that if in case you can find a point in a polyhedron which has all which satisfies all constraints defining it as, or inequalities as strict inequalities, then it is a solid, and we say that it is the same dimension as the number of variables defining it. So dimension P is 3, right? And we continue with this example. So I am now saying that you consider the hyperplane H1, which is all points x in R3, so that x2 is 2. Okay. If you take this hyperplane, then obviously we get two half spaces, right? One would be x2 greater than or equal to 2, and the other would be x2 less than or equal to 2. Let me consider the half space x2 greater than or equal to 2. Then you see that x2 greater than 2 is this side, and P does not lie on it, right? And then I am saying that now you consider the intersection of P with this half space, and this comes out to be region ABC, right? Because the half space contains x2 equal to 2 also, and this is your hyperplane H1, right? And x2 equal to 2 is satisfied by points on the polytope, right? So when you take this intersection, of course, so here I am saying non-empty, and then this comes out to be the region ABC, right? You see that this is the region, because every point on this triangle has x2 equal to 2. You can check that. Yeah, convex combination of every point here of these 3 points will again have x2 equal to 2, because all the extreme points have the second coordinate equal to 2. So you can see that very well, and so this is the region ABC, and this is a part of H1. So from our definition of a face of a polytope, if I can find a hyperplane such that this definition is satisfied, then this is a face of P, and by our definition, the dimension of ABC, this would be 3 minus 1, because this is it is in a hyperplane H1, or you can say that x 2 equal to 2 is the this is the inequality which is satisfied as equality by all points on the region ABC, and therefore, this is a facet of dimension, it is a face of dimension 3 minus 1 which is 2, and so it is a facet, right. Now, in my definition earlier when I had talked about a supporting hyperplane, and so here you will say that x 2 equal to 2, H 1 is a supporting hyperplane to the polytope P, right. Now, in my definition, if I take the half space to be x 2 less than or equal to 2, then P would be in that half space, and therefore, I do not have to write this. So, please check that in the when I was defining a concept of a face and face of a polyhedron and the supporting hyperplane, I may have not mentioned not equal to, but see the understanding is that if you are taking the half space in which P lies, then obviously this will not be empty, P intersection H S 1. So, the whole idea I am trying to show you is that you take a half space and you take a polytope, then the two just meet in this face, right, ABC, and that is the whole idea. So, whether you take the half space in which P lies or which P does not lie does not matter, but basically they will intersect at that face of the polytope, right. Now, similarly, let us take another dimensional face of the polytope P. So, if you consider the edge AB. So, I am taking two different definitions and trying to show you. So, now it is the intersection of the inequalities 2 x 1 plus x 2 equal to 6 and x 2 equal to 2. You can see from the diagram. Also, that means every point on the line segment AB satisfies the second and the third inequalities as equalities. Okay. And so, by definition we had two definitions of the so by the dimension of the line segment AB is 3 minus 2, because two linearly independent inequalities they are being satisfied as equalities, and the dimension of the polytope we had said is 3. So, it is 3 minus 2 which is 1. So, therefore, this will be an edge of the polytope, right, by our definition. But now, here I also want to show you that you can construct a supporting hyperplane, and therefore, it will be a face. So, the supporting hyperplane I am saying consider the hyperplane x 2 minus x 3 equal to 2, right. Then you can again see that for x 2 minus x 3 greater than or equal to 2 for all point, I mean if you take the half space this, then P does not lie in this half space, and therefore, and the intersection of this half space with P is the line segment AB which lies in H 2, right. And so, again AB is a face of P by our definition, right, and the dimension as we said, because two inequalities are being satisfied as equality. So, therefore, the dimension of this face is 1, right. And now, you consider the point A which is 2 comma 2 comma 0, this is the point of the polytope, and this is a vertex, and so we must have 3 inequalities that are satisfied as equalities by the point A. So, you look at these 3, and therefore, the dimension of this vertex is 0, which is what it should be. That is why we call it a vertex. And again, just for the fun, see, you can also try to construct some other hyperplane which is a supporting hyperplane to the polytope at the edge AB, then or for some other edge AB, and then here for the hyperplane H 3 for 4 x 1 plus 3 x 2 equal to 14, you see that the point A satisfies this as equality, right, and intersection of the half space P intersection H 3, where of course, here again I am taking the half space to be greater than or equal to 14, then the intersection is the point 220, and this will be this is contained in H 3. Therefore, A is the face of P and the dimension is 1. So, therefore, now you can do the same exercise for all other edges, like for example, this is an edge, this is an edge. So, try to construct supporting hyperplanes at these vertices as well as for the edges, and see that show that, for example, x 3 equal to 3 is a facet of this polytope, which you can also sit down and show that you consider the hyperplane x 3 equal to 3 and so on. So, I think this should give you a good idea about the how to determine the dimensions of faces or different faces of a polytope, and the important kind of faces that we will be using when we want to give a geometrical picture of the simplex algorithm, which are the extreme points or the vertices and the facets supporting hyperplanes